Thank you everyone for joining in. I am Radu Mazilu. I'm a senior DevOps engineer at Cognizant Softvision, which means that I play around with a lot of different technologies. I break and I fix things, and I really enjoy cloud environments and having them written in code because I don't like to repeat myself. So what we're going to talk today is about how we implemented the disaster recovery solution for one of our clients. But before going into that, I'm just gonna paint a bit of a picture of what a disaster recovery solution typically looks like. So you have your servers that are in a data center, okay? So, or in a cloud environment, they are in a region, in a US East 1 or West or whatever. In order to be able to handle the scenario where one data center or one region goes down, you need to have resources deployed or at least ready to deploy in a second data center or region. What this usually means is that you have two big scenarios. Either you have servers that are running there, just sitting idle for the case where you need to make the switch to that other data center. In this case, you can switch very fast, but you also need to pay for those idle resources, or you decide to cut on costs. Those servers are not running, they are shut off or ready to be deployed from your infrastructure as code. In that scenario, it costs you less, but the downtime is bigger because you need to wait for the servers to boot up. Besides that, there's also data synchronization that you need to take into account for, so databases or static resources, that kind of stuff. So it's not an easy to maintain, to build and maintain solution, and it's not cheap as well, depending on how much downtime you can take before having a business issue. All right, so this kind of this is the picture of the traditional disaster recovery solutions. What I also want to say before I boot up this discussion is that we're for this client, we're using AWS. The first question that pops in mind for a lot of people when you hear about disaster recovery solutions in cloud is when's the cloud gonna go down, right? Because a lot of resources and websites are hosted on it, and it's not gonna go down, right? Because there are a lot of brilliant people out there. Well, for AWS, I looked into, but I'm sure it applies to the other providers as well. There were two outages just this year. One in January for the entire region of US East 1, and another one was smaller in August for US West 2. They had a network problem there, which blew our latencies out of the ballpark. So my point here is that it does happen, whether it impacts all their services or just a portion of them. Disasters are gonna happen, so you'd better be prepared. Now, in the first part of this presentation, I'm going to talk about the actual application that we built. That is relevant because you might ask yourself, well, what do I do in the case you're talking just about serverless, but I'm not using serverless because it doesn't suit me. Well, this is about how it suited us and why we got to a serverless solution and why it works for us. Afterwards, we go to the second part where we talk about the DR solution, and you'll see that it's much easier to implement a disaster recovery solution when you are using a serverless environment and serverless application. And lastly, a very interesting bit is testing the disaster recovery solution. Because if you just put it there, it probably won't work as well when you actually need it, and then you'll have to debug it when you need it, and it's gonna be a tough time. So testing it is a very good idea, and as you'll see later, it actually helped us discover quite a big bug. Okay, so for the first part, the application. Our client needed a solution that exposes internal APIs for external clients, okay? So it needed to handle authentication and authorization. It needed to handle billing the clients for the request that they make. So it needs a solution that counts every request for every external client. And it also needed to be extensible. Because it started out small and it got pretty big in the process. Now, as you can see, the cost of this service is sort of shifted towards the external clients, and that's why the serverless model worked very well for this situation, because for serverless resources, most of the time you pay for what you use. I'm talking here about AWS Lambda, API Gateway, DynamoDB as the basic stack. So that means if the clients are making a lot of calls, then they pay you a lot of money, and you need to pay a proportionally size of that money to AWS. But if they don't make calls, maybe they're on vacation, then you don't pay anything to AWS. So basically, you don't have a headache regarding costs because of that. That setup. And it's also automatically scalable. It uses multiple availability zones out of the box. So it's pretty easy to maintain, and it's highly available without you having to do much about it. Highly available, but not disaster recovery proof. Okay, so this is a big overview of how we're running things here. You have here a subscriber that uses some APIs from what we offer, the authentication component. You have a gateway with various components, authorizer, DynamoDB, Elasticsearch, S3, Kafka, whatever we have here. This is what we built, and in the back you have the source system, the internal APIs, a data lake, the billing system, subscription management, and whatnot. These are internal resources that need to be protected from the outside world. So this is where we come in. And this is sort of a finer image of an API that we built so that you can see how we piece together several AWS services. So it works and it's all scalable out of the box, because we use API gateways, various lambdas that we combine using step functions. We use some Elasticsearch. That's the only component, or actually one of the two components that don't scale out of the box, but it's works as a data store. So but it's not crucial to the functioning of the APIs. So if this goes down, we're just gonna have a problem on the short term with counting the requests, but the APIs will continue to function. S3 is of course scalable as well, and you get the pictures. In this example, we have an API that stores images. You can send those through APIs or a file-based client. So That's pretty much how it works. These are the components that we use for all our services: API Gateway, AWS Lambda, DynamoDB for storing, S-Tray for static files, step functions for piecing together an import process, for example, and Elasticsearch for storing and looking through usage events if needed. And by usage events, I refer to individual API calls that the external clients make. Okay, so you got the point with the with how the application looks like and what components it uses. Now let's talk about the disaster recovery solution. So go through the diagram. We have here the production domain. Okay, so you have the URL there that can point to a region. So this is the final solution that we implemented. All right, and I'll go through the steps we went through after that. So the point was to have the main region that has all these components. These are Lambdas, okay, with various services, config services, parts services, vehicles, different names that make sense to our team. All right, you have DynamoDB here and the Elasticsearch cluster. And the point here is that we have the Lambdas deployed to the second region as well. We use global DynamoDB tables to synchronize data. So DynamoDB has an out-of-the-box replication service, and you just need to tell it, okay, write to this other region as well. And it's multi-master as well. So you can write in this region and it will be synchronized into the main region. It's not only read-only. For Elasticsearch, the synchronization is a bit more complicated. It's not supported out of the box. We use an S3 bucket where we store snapshots. We replicate that to the other region. It's not as real-time as DynamoDB is. There, we could have implemented something more real-time, but as I said, Elasticsearch is not crucial to the functioning of our application. It's more used for analytics. Okay, so what this solution provides is the data is synchronized to the other region with DynamoDB and Elasticsearch. Business logic is kept up to date. What this means is that when we update the code for the Lambdas in the main region, we also do it for the secondary region. So in the event of a switchover, we have everything up to date, up to speed. Resources on the disaster recovery region are on demand only, which means no Lambda provision concurrency, so everything just kind of slips there. But at the same time, it's ready to process requests. But if no requests come to this region, you pay basically nothing for it. That's why the cost is almost zero. Right? So for both Lambda and DynamoDB, you pay only what you use. And of course, we pay for the storage. You can't make it really zero. It's almost zero cost. And the time to recovery is zero for most APIs. And why is that? Is because the Lambdas are deployed in the secondary region as well, and they don't need anything to be functional. They just sit there. And if we switch all the traffic to the secondary region, then AWS will automatically scale in the background to however many Lambda instances we need. And it's just gonna work. Why the time to recovery is zero for most APIs, not all of them, is because we have components that is REST proxy to a Kafka cluster, and that component uses containers because it maintains active connections to the cluster. And for the disaster recovery region, we keep those shut down for cost reasons. And the point is that after you boot them up, you'll have those APIs working as well. So everything is working. You'll see more about that in the disaster recovery test portion of the presentation. Okay. What I wanted to also include in this presentation, because I like to dabble a bit in the non-technical side of things as well, is how we actually developed this and how we sold it to the client. So if you present a solution that you approximate it's gonna take X months, I don't know, half a year to develop, and you'll be telling the client that, okay, next half year I work on this disaster recovery solution that maybe you need, maybe you want. So the other stuff you need developed, it's gonna be delayed, but if AWS fails to function, you'll have no downtime. He might be sold, but he might not be sold on this kind of a big project. So what we did was actually break up the entire project into smaller pieces. We also work in Agile Scrum, so this worked very well with our methodology. And we said, okay, we first develop this piece, we show you it works, you can present it to your managers or shareholders or whatever, and then we go to the next and so forth, and we break up the effort, and you can see results, and it will be easier to digest this way. And of course, the client was more excited about this variant than just working on the entire solution at once. So in phase one, it was kind of a proof of concept. We only did this for a stack, which means a collection of 5 to 10 lambdas that are related from a business point of view. And we implemented what I discussed previously. We deployed the lambdas to both regions, enabled replication for DynamoDB, and we started sending requests to the first region, and then we switched to the second region, and we compared the results. We checked that every request is successful, and that the global count, that's very important for billing our the clients. The global request count is correct. In phase two of the development process, we configured, we optimized the cost, because for some lambdas we use provision concurrency so that we don't have startup times. And what we wanted to do here is include in the infrastructure as code, we use Terraform, includes sort of including the code that we want on the secondary region to not have anything provisioned, anything that has add costs, and just leave everything for pay-as-you-go option. We configured all the tables to replicate all the tables that needed to be replicated, and we also configured replication for Elasticsearch. In phase three, we went full scale. We configured, updated the code for every stack. So that means about 50 repositories in our case. We deployed everything to the disaster recovery region. We configured our deployment tool to also sync that region for every deployment, so we don't forget about it. And also configure and test the Kafka proxy I told you about, the service that runs on containers. And last but not least, the phase 4 of our development process was actually configuring the failover from Route 53. That means having a health check in the DNS service that can start the failover. We can also do this manually. So if you have actually AWS services that go down, then you can make the decision to switch automatically. That's what we did. But if you have something that is related to other services that you use, then you can make a manual decision as well. We also did a simulation of a failover manually this time. For the first time, we wanted to do manual checks and failovers and whatnot. And we also developed and used in this stage the automated tests for that I described earlier, and I'll present later. So a set of scripts that kind of go through the entire process of simulating a failover and afterwards the failback. Okay, so this was our development process. We broke it down into pieces. We started small with a proof of concept. We extended step by step until we got to the full solution, and of course testing it, because if it's not tested, you have no proof that it actually works. And I'm gonna we got to the third part of this presentation, which is the disaster recovery test. As I said earlier, this is very important because if you need to test this when the development is done, but of course you need to test the disaster recovery solution periodically, because each deployment, each feature that you add needs to be also synchronized to the disaster recovery region. And if you don't check it, you might if you don't test it periodically, you might have the surprise that your beautifully implemented disaster recovery solution actually doesn't work anymore, or just a part of it works. So it's all down the drain. So the steps of our disaster recovery test, automated test, are as follows. We start simulating traffic. So of course this is for this happens on development or QA, not in production, because we don't want to actually mess with production, but the entire infrastructure is identical in QA and production, so it does work just as well. We use Apache JMeter to start sending requests. We simulate the failover, and we bring up the infrastructure and some more steps on the next slide. But what I wanted to point out here is that Apache JMeter, for who doesn't know, can simulate. It's a load testing tool. We didn't want to load test. We just wanted to send requests, so it suited us well. And for this automatic test, we selected 5 of our most used APIs. We don't do this for all the APIs. We don't have full coverage if you want, because it would be very time consuming, and you need to juggle around it with costs and effort. We simulate failover. This could be done from Route 53, but we had some limitations there from the client, so we switched from JMeter, the endpoint. And at that point, when we start sending traffic to the secondary region, we start spinning up disaster recovery infrastructure. Just a small piece, because as I said, the Lambda DBs and API gateways are already there. DynamoDB was already there. What we need to get up is the container with the Kafka proxy and the Elasticsearch cluster. We do this using Terraform. We don't like doing manual stuff. So it's just a command that's executed from the automated test, and it boots up the infrastructure. Now, after we sent traffic to the disaster recovery region for a while, we also need to test, of course, that we can actually fail back without issues. We can switch back to the main region. We do that by changing the endpoint as well. And afterwards, automatically as well, we start bringing down the infrastructure that we booted up earlier. So we are careful with the costs. Elasticsearch data is some part of the Elasticsearch data is lost in the process because, as I said, we don't need real-time synchronization, but we can recover all the usage events from CloudWatch. And the validation of the test, and this is very important, is actually checking that the number of requests sent by JMeter is the same as what we have in DynamoDB and Elasticsearch. JMeter, of course, knows how many requests it sent. That would be, it's a simulation of a client. DynamoDB and Elasticsearch is where we keep our counters. In DynamoDB, it's just a counter. In Elasticsearch, it's actually all the usage events stored with all the data. So this is sort of the overview of what the test does. Pretty predictable, probably. It fails over and fails back. But it's important to kind of see how we did it. And next up, I wanted to present you actually how such a test went down. You can see a Grafana chart with actual data. We have failover and failback marked up here. We did this, so we did 2 failbacks for this for this test, but we also did longer tests running for 6-7 hours of just switching back and forth for half an hour of each region to check if we can rely on doing this multiple times. With green, you have the successful requests. Yellow marks the unsuccessful requests. And this was relevant because, as I said, some of the APIs don't work out of the box because we have to bring up the ECS containers. But it takes a pretty short time to boot up those containers. And then afterwards, you can see that all the traffic is back to successful. The failback runs flawlessly because the data is still there. Lambdas are all up to speed, and the containers are not brought down because it's the main region. We don't save costs there. And this goes on and on. You can also see a bit of number of requests here, number of errors. This is kind of how it looks like. For most of the APIs, we'll have a successful failover with no downtime. And for those sensible to the ECS containers, we have approximately 15 minutes downtime, which in the event of an entire region going down in the AWS, because that's what we prefer for, and that's what happened this year, 15 minutes it's pretty manageable for only some of the APIs. Of course, if we want to optimize this, we can just keep the ECS containers running in the secondary region as well, and then we'll have absolutely no downtime. And this is an example of the counting of the requests, as I said, from JMeter, DynamoDB, and Elasticsearch. And of course, these should match to perfection. Okay, so we went through the entire story, how it's the happy path, how everything works well, and it's all flower and rainbows and sunshine. But I also wanted to share a bit with you some of the an example of a problem that we discovered. And it's actually the disaster recovery test that helped us identify it. So in order to be able to explain you this bug, I need to present just a bit how our system works. So this is the component that actually counts the requests. The API, the Lambdas write logs to CloudWatch. From CloudWatch, we have a subscription filter. It's a service from AWS that scans the logs, and when it sees a log message that matches a pattern, it can trigger another Lambda or do something else, but for us, trigger a Lambda. And we get the usage metrics Lambda that then writes to DynamoDB, increases the counter, and writes the usage event to Elasticsearch. Pretty straightforward, right? But while running the test, I had the surprise that everything worked well. But instead of seeing 1,000 requests in JMeter, for example, 1,000 requests in JMeter, DynamoDB, and Elasticsearch, I saw 1,000 in JMeter, of course, 0 in Elasticsearch. That was expected because I knew there was a problem with Elasticsearch when I ran that. But in DynamoDB, there were 3,000 requests. So that was interesting. That meant in a real case scenario that we would bill the clients of our clients 3 times as much. So it's kind of a big issue. Initially, I thought that maybe it's ran more than it should, the usage event metrics Lambda. But actually, what I discovered is that the Lambda was retried 3 times. When the connection to Elasticsearch failed, there was an exception. True, that was not. It was not caught by intention because we want the exception to be captured in the logs and trigger an alarm. But that signaled to AWS that the entire Lambda failed, and that meant for AWS, okay, let's retry this. By default, it retries 3 times. However, before failing, the usage event metrics Lambda was successfully writing to DynamoDB because this is really fast. This is faster than Elasticsearch. So what happened is that a usage event metrics was received. It wrote to DynamoDB, increased the counter, tried to write to Elasticsearch, did not manage to do so, and retried. Got again to the Lambda, wrote again, Elasticsearch no, and retry. And that's how our counters were 3 times bigger than what we should have had. So that's something to keep in mind. For these types of situations where Lambdas are triggered asynchronously from different points, in this example, the subscription filter, you have by default a retry count. So AWS will retry by default to launch your Lambda if it fails. Of course, this is configurable, and this is what we did. We said, okay, we don't want to retry if the usage event is not being processed, we want to write it to an SQS queue that we didn't, I didn't include here, and look at it later. But please don't write to DynamoDB 3 times as much as you should. All right, so I talked to you about how a disaster recovery solution looks in this kind of environment. What are the advantages of it? I repeat myself because I really like that it's no downtime and very little cost. We also talked about how we tested it and what's the advantages of having an automated test that you can repeat periodically. I also showed you a bug that we caught doing this, and I found quite interesting. What I'm going to show you next is our plan for improvement, because as always, there's room for improvement with every solution. What we want to do next for our setup is not have failover solution, so that you can switch to another region when it fails, because that is prone to a discussion. Maybe the health check doesn't catch an error. Maybe you don't switch over at times. You still have to test it. You have to make sure that it works. It's still a bit of maintenance, and maybe you have some downtime. So what we thought we should do next is actually have the application run in 2 regions at the same time. Doing so will increase costs, clearly, because you have to run those containers and Elasticsearch cluster at the same time. But it also means that if an entire region goes down, the end users won't even know that something happened, because the request will be automatically handled by the second region. It's something. It's big thing that you could say for your solution, that it can take an entire region or failed AWS going down. However, trying to do so comes with some challenges. And of course, when you are talking about distributed databases such as DynamoDB, you are going to have to talk about conflict management, because what DynamoDB does is it guarantees that inside the region you can write to it, and it will always respect the order in which you wrote, and your data will practically be safe and sound as you expect it to be. However, between regions, there's no such guarantee. So if you write to both regions at the same time, the servers, the database servers in the background, will have to to synchronize, and at some point they'll have a conflict, and the region 1 will say, okay, so this counter is 2, and this one will say, no, it's 4. And who wins? Well, it's kind of hard to decide. There are a number of algorithms that can decide who wins. I won't get into this because this is database related. You can look into it, but basically none of it is perfect. All have some drawbacks. In the case of DynamoDB, the conflict management algorithm is last right wins, which does what you would guess it does. Whoever has newer timestamp wins. Elasticsearch replication is also challenging. So our solution was maybe not the most cost efficient, but the less error prone and simple. So we have two independent Elasticsearch clusters, and we write to both at the same time. And what we also need to take into consideration is how we handle all the systems working in parallel. For example, we have an import process that contacts an external API, marks what we processed from their entries, and writes to a third party. And of course, how do you decide which region should do that? How do you handle that when that region maybe goes down? Because you can't have that import process running in both regions at the same time. So this is sort of an example. But yeah, the conclusion here is that we could have absolutely zero downtime with a bit more costs and with some development to do. However, we could then say that, oh, US East 1 went down. I didn't care. Yeah, so that's what the future sounds like for our solution. Short recap. We designed a disaster recovery solution that is cost efficient, has no downtime for most APIs, developed in phases to keep the impact low. It has automated tests that I definitely recommend, and we want to keep improving it. Of course, this is also about how this serverless environment allows you to develop disaster recovery solution that has these advantages. So yeah, I'm a fan of this kind of environment with API Gateway and Lambdas. Of course, it has its uses. It's not good for everything, but for where it's fit, it's a really, really good fit with big advantages. Okay, so do we have any questions?
Yes, of course. But first of all, congrats for the presentation. I mean, I really enjoyed the walkthrough, the reasoning, the explanations that you provided, and yeah, I'm satisfied. I've learned something new today. Yay!
Thank
How
you.
about you, Dan?
I knew you were paying attention.
Yes, I'm doing because and I'm interested because I had a similar thing to do. Well, this season, and I would have used some inspiration from your presentation if that was, prior to my task or mission. Next time I'll call you.
Next time.
Next time when I have a difficult problem, I'll call you, Radu.
You do
Maybe
so.
you've got
Yeah, it's always good to exchange experience, right? Share knowledge.
And if you don't have questions, Florin, our audience definitely has questions. So there are a few. I'm gonna highlight them one by one. This one, on what event base do you switch back to the original region?
Switching back to the original regions is not automatically. We do a manual human decision because in our experience, you need to make a human call. Okay, you can't really rely on the AWS status page, for example. It's notoriously delayed, and we like to make checks that everything is all right before we fell back.
Well, yeah, makes sense.
Could you elaborate a little bit on the terms of failover and fallback?
So failover is when we switch from the main region to the secondary region, and failback is when we fail back from the secondary region to the main one.
Thank you.
You win again. All right, the next one. If you encountered any issues related to different Lambda deployment model?
Different Lambda. No. No, we didn't have any issues related to deployment. We do our deployments with Terraform. We have some Lambdas with provision concurrency and some with not. And we didn't have any issues with it.
All right, and the third one, also from Bogdan.
So how fast is the failover switching traffic to backup data center since you're using DNS failover? This is known to be quite problematic due to caching.
I will firstly admit that I'm not an expert on Route 53. We basically rely on AWS to handle that. We configure both regions in the Route 53 configuration. It has a failover routing policy, and when the main region goes down, or we say it goes down, it handles that in the back for us.
Mm-hmm. But overall, you mentioned some measurements of, if I recall well, 15 minutes or something, or?
That's just for our not so serverless components to boot up. Okay, so for containers, we didn't measure the DNS caching.
Mm-hmm. Mm-hmm.
All right, cool. Thanks a lot, and it was clockwork, I would say, including the questions. Brilliant.
Okay, I would like to share my screen a bit again because I have my my contact details there. Sure. If somebody maybe has a late question that they want to pose there, you can find me on LinkedIn or write me at my predictable email address. I'll count to 3 before switching to the next slide.
I've just sent you an email, Radu.
So Florian was very quick.
Great.
I'll stay in touch.
I reply, sure.
And then we'll also publish the talk, and this will be visible, so people can definitely reach out.
Radu, thanks again for your contribution at Codecamp, and we're looking forward to having you next time.
Thank you. You can also see more DevOps presentations at the event we had inside Cognizant Softvision Programmers Week. Google it or scan it. And last but not least, a big thank you.
Thank you too.
Thank you as well, Radu. And yeah, see you next time. And until the next session, I think we have 12-13 minutes break. And yeah, everybody get a cup of coffee, do some stretching.
Yes.
It's been a pleasure. Great being here. I really like you guys. I really enjoy your energy. Keep it up.
Thank you so much.
And, yeah, let's hear each other again. Goodbye.
Yeah.
Have a great day.
Let's do that. Have a nice day.